We're ready to look at our next functional group, which is the carboxylic acid. The carboxylic acid has got our C double bond O and then also an OH right next to it. Now you see it represented two different ways here on the screen. With the C double bond O and the OH, it's really easy to see that that's a carboxylic acid. We got used to that. But we also need to recognize the carboxylic acid when it's written out like you see on the second part, just COOH, because this is so much easier to do. If you were somebody sitting there trying to type out the formula of something, it's a lot easier to do COOH than it is to try to figure out how to draw that out when you're just typing away. So this is very, very, very common, and you ought to, as soon as you see that, associate it with what you're seeing up at the top, the carboxylic acid. Okay, so I told you that if you took an alcohol and oxidized it, it would either make an aldehyde or a ketone, because it is exposed to oxygen, automatically converts to that. But if you were to take this aldehyde and expose it, it works for the aldehyde, expose it to oxygen some more, it could be converted to the carboxylic acid. And that's what this is stating under here. They are producing these, that's how you make carboxylic acids. You just take an alcohol, expose it to oxygen, and it will readily, easily convert to carboxylic acid. So alcohols, drinking alcohols, a wine can turn sour with time because that's a property of alcohol, of carboxylic acids. They are sour to the taste. So that is the end game of exposing any alcohol to the oxygen in the air. Okay, we can now, of course I just did up there at the top, we can order those things in terms of increasing oxidation state. I did not include the hydrocarbons, but hydrocarbons have no oxygen, so that is not a high oxidation state, it's a low, okay? Alcohols are a little bit more. Exposed to more oxygen, it can turn into the aldehydes or the ketones depending on where the OH group of the alcohol was located. And then if we go a little bit further, it turns into a carboxylic acid, maybe an ester, but not by just exposure to oxygen. We'll talk about how to make esters later. Keep on oxidizing. The end game is carbon dioxide. So anything that you consume that contains these guys will, through the process of the metabolism in our body and exposure to oxygen that we're bringing into our body by breathing, will eventually get converted as the end game to that carbon dioxide. So that is the ultimate oxidation of anything that is carbon-based when it goes through the process. All right, so carboxylic acids are acids. And a unique property, it's not unique, but it is a big property of anything that's an acid, is when you take it and dissolve it in water, it will release those H's off of the end. So let me draw a carboxylic acid up here in the top. When you take that compound and you place it into water, so I'll just represent that as I'm putting it into water, what happens is and there's carbons over here or H's over here. What happens is the O stays attached and an H pops off, and it pops off and leaves its electrons behind. So we end up with an H plus cation, and this thing is an anion, and that is what happens, producing those two things. And it will always lend itself to us tasting sour. So our sour taste buds pick up on that, the fact that when it hits our tongue and dissolves and breaks apart like that, it will signal our sour taste buds. I've got a box around this one image here because I want you to know that trend. If you take things and oxidize them, that is the level of oxidation. As they get more and more exposed to oxygen, it will eventually go through those sets until it gets to carbon dioxide. So let's talk about the various kinds of carboxylic acids, starting with the simplest one and working our way up a little bit from there. The simplest carboxylic acid only has the carbon associated with the C double bond O, okay? So the simplest one would be formic acid. So you notice that we've got the C double bond O, the OH, and we have no other carbons. That's formic acid. This would be the simple way to represent that. Now, if we dissolve that in water, it's this hydrogen that can pop off. It's not the other hydrogen. It's attached very tightly. Now, where would you see or come across formic acid in the world? Well, if you have ever been bit by an ant and it burned, it hurt, fire ant, or got stung by a bee or a wasp, that is the typical chemical that they pump in there that hurts, that burns. This is what formic acid is. Going up from formic acid is acetic acid. If you replace the hydrogen that was in formic acid with a carbon, and then of course we have all of those, this is what we call a methyl group attached there, then this is going to be acetic acid. Now that's its common name, but it's the name that everybody calls it. We rarely would call this by its IUPAC name. Acetic acid is the acid found in vinegar. When you take any drinking alcohol, which is ethanol, and expose it to the air, it will first turn into an aldehyde and then it will turn into a carboxylic acid. So if you go to the grocery store and you buy vinegar, you're going to see vinegars like red wine vinegar. How did that happen? Well, they took red wine and they converted it. They just exposed it to the air. It would naturally turn into red wine vinegar. Apple cider vinegar. So you take apples, they ferment, they make alcohol. So you might have had a hard cider or seen hard ciders out there. These are ones that have been fermented and turned into alcohol, and then you keep exposing that to the air and it'll eventually turn into apple cider vinegar. So any of these things will eventually, as they get exposed to the air, that's the oxygen in the air, is going to be converted to this form of acid, acetic acid. So we use that a lot in cooking, and you can buy it not being made by things that get flavors, so just a plain distilled vinegar, a white vinegar, it's not going to have the flavors from the other things, but will still have the sour taste of the acetic acid. When you drink alcohol, not you, but in general, when alcohol is consumed, it is going to first get converted to aldehydes, but then in our body get converted to acids as well. So ethanol turns to aldehydes, not to ketones, because the OH is on the end carbon, then acetic acid, and then, as we have discussed when we talked about alcohols in a former lesson, eventually carbon dioxide and water by enzymes in the liver. It's the aldehydes that give that headache. It gives you the hangover. So we don't like the aldehyde that is produced by the alcohol. Now, why is methanol such a bad thing? The methanol, we said, would cause blindness. Methanol can cause blindness because it is going to generate the formaldehyde. Okay, so methanol, CH3OH. That is methanol. If it gets oxidized, it's going to get oxidized into that one carbon gets the double bond. It has the H and it has the other. Shoot, I can't write. Let's try that again, everybody. Okay, it's got the C. That C ends up with a double bond O. So that is the formaldehyde, and that is the part that's going to react with the proteins in the eye, and that's what's going to cause the blindness. So that is why it is very important that if you consume alcohol, that it is not methanol. Now, some carboxylic acids aren't just a little bit sour, but have a really awful smell. When that carbon group gets really, really long, okay, those end up giving us really, really bad smells. So we can have foot odors kind of smell. Cheeses that have really pungent smells might have these long chain carbons. Now, some people like Limburger cheese, but I understand that it has got a really pungent smell to it. So the molecules that have these long chains can get up into your nose and you can smell them, and a lot of them have really bad smells. Okay, I would not associate this really with a bad smell. I mean, the acetic acid, but propanoic acid and acetic acid is what gives Swiss cheese, for example, its characteristic smell. So it's not really pungent and bad, but when that carbon group gets longer and longer, then it starts getting more foul. Okay. I've never kept butter around long enough to get rancid. I keep butter in the refrigerator, which keeps this from happening. But butter can be converted to carboxylic acids, and they have long carbon chains, and those long carbon chains, this one is now getting up to 4 here, is going to give butter its bad smell. Now, there's some carboxylic acids that are called alpha hydroxy acids. So let's see what we mean by that. Here is, let's zoom in on this tartaric acid a little bit here. All right, here is that carboxylic acid group that you can see there. Let's see if I can make my hand do its thing. Oh yes. Oh no, I don't know how this works. Okay, so we see our carboxylic acid group here. This carbon right here is called the alpha carbon because it is the first Greek letter, right? So we've got right here is the alpha, this is the beta carbon, and so forth. So right next to it is an OH group. That's called an alpha hydroxy carboxylic acid. If we look from the other direction, we see the carboxylic acid group right next door. This is its alpha, and it has an OH group. So that is tartaric acid, and that is an alpha hydroxy. Lactic acid, also a alpha hydroxy. We've got our OH group here. This is the alpha carbon next to the OH group. Carboxylic acid group here. This is the alpha carbon with its OH group attached. Okay, let's see what's next. Citric acid. Zoom in on the citric acid there. In the citric acid, we've got, where's our alpha? There we go. We have a carboxylic acid right here. This is an alpha carbon to it, and it has an OH group right next to it. So that would be it. Now, does it have an alpha next to this one? No, there's no OH group there. Does it have an alpha next to this one? No, there's no OH group here. But it's an alpha hydroxy because of this group, and this is the alpha carbon, and there you go. I got one more. Malic acid, which is found in apples, is right here, and we'll zoom in. No, we won't. Malic acid. I want to try one more time. There we go. Malic acid. We've got our carboxylic acid group. We've got our alpha carbon and an OH group right next to it. Now, do I want you to memorize those formulas? No, but I would like for you to be able to recognize an alpha hydroxy group when you see one. And there's a lot of compounds out there that utilize alpha hydroxy carboxylic acids. You might even hear advertisements about skincare creams that have alpha hydroxy acids in them, and they're supposed to have features that are good for your skin. So that concludes our discussion about carboxylic acids.